Okay, let's get started on the fields worksheet. Question number 1. It says, what would the force of gravity be on a 300 kilogram ship that's 35,000 kilometers above the Earth? Okay, number 1, first thing you gotta do is find out how far from the center of the Earth. So we got the Earth thing is 6,380 kilometers, is this little one. And then we have 35,000 kilometers, which is the distance into space. So my total radius would be 35,000. 6,380 gives me 41,380 kilometers, but we don't want kilometers, we want meters. And the force of gravity will equal G m1 m2 over r squared. 6.67 times 10 to the minus 11 mass of the object. Let's do the Earth first. 5.98 times 10 to the 24 and a 300 kilogram ship. That's going to be all over 4138000 squared. And let's do the math on that. Okay, there's my denominator. Maybe I'll square that, invert that. Now we'll go times 300 times 5.9824 and then divide. And I get 69.9. We're pretty close to 70 if we round that off. Let's take a look at question 2. 2 says, we got someone space station 400 kilometers up in the space. Okay. Again, we got the Earth and the little 400 there, so 6,380 kilometers plus 400 kilometers equals 6,380 plus 400, 6,780 kilometers. Let's make that meters. The time it takes to do one orbit is 4 pi squared r cubed all over top of gm. You might as well memorize that one. You could derive it because the centripetal acceleration will equal the force of gravity. So this guy will equal mv squared over r. Rearrange it, solve for t, but there is no t. You'd have to put the circle dynamics in, but maybe I'll just memorize it for the sake here. So we got 4 pi squared 6780 1 2 3 cubed all over top of, and the mass is the Earth. And square root that whole thing. So now it's just a big calculator fun. 4 pi squared, multiply by that. I get that 670 multiplied by 1,000. There's my radius in meters, so I got to cube that. Multiply by that. So I have the numerator now, 6.67 exponent 11 change sign. Divide by that, divide by the mass of the planet. Get this huge number, and then I square root that, and I get 5,554 seconds. And do I divide that by 60? You're looking at 92.5 minutes. Should be pretty cool. You get to see the whole Earth every hour and a half. Okay, number 3. 3 is a good old vector question. No, hold on, let's do number 3. 3, two charged objects are 15 centimeters apart. 2.7 times 10 to the minus 5. 2.7 times 10 to the minus 5. Both the same charge. The distance from center to center is 0.15 meters. Force of electrostatics, K, Q1, Q2 over r squared. Looks a lot like gravity all over again. 8.99 times 10 to the 9. 2.7 times 10 to the minus 5. You just gotta write it down twice, or I'm just gonna pull out some cool math stuff and just say squared. Okay. 8.99 exponent 9. 2.7 exponent 5 change sign. Square that guy, multiply him up, and divide it by 0.15 squared. Gives me 291 newtons. Okay, that's the force between those two guys, and they're both positive charges, so they're going to repel. Okay, here's number 4. That's the vector question. So we're going to have a triangle, which is 3 meters by 4 meters. And then this guy here on the angle will be 5 meters. It's a 3, 4, 5 triangle. And there's a charge on every corner. And so this guy is going to be repelling from him. He's going to push that way. This guy's even closer. He's only 3 meters. He's going to be repelled the longest one. That's a 5 meter one. That's going to be the shortest one. And you can fill these guys in. If you want to call this number 1, 2, 3. We'll just keep ourselves organized here. Number 1. Okay. Every single position, same charge. All the same charge. The tops can be the same. The only thing that's going to change is your denominator here. So my top is 8.99 times 10 to the 9. And the charge, they're all the same charge. 8.6 times 10 to the minus 4 squared, all over top of r squared. R squared in one time is going to be 4. Let's see, the first one's going to be 3. Second one's going to be 5. And the third one's going to be 4. So let's go 3 squared. Let's do the top. 8.99 exponent 9. 8.6 exponent 4. Change signs. Squared. Multiply together. There's my top. It's 6649 over top of 3 squared. There's 0.4. It's a couple decimal spots in there, but you can store that in your calculator. Stick it in the memory. I'm going to divide that by 9. And we got 738.8, which is this guy here. Number 2, I just take the number I have in my calculator that I stored, 6649004. Instead of dividing by 9, I'm going to divide by 5 squared. So that one will be 265.96. And number 3, you could even work yourself backwards, say, times that by 25, I'm back to the number on the top again. But this one, number 3, I have to divide by 4 squared, which is 16. That's going to give me 415.56. Okay, and then we're going to do components now. Finish this question off. I need this angle in here, though. That's the same as this angle here. That's going to be 3 divided by 4. Inverse tan. 3 divided by 4 is 0.75 inverse tan. I got 36.86 degrees. I need that one to figure this out, but the first one's fine. Number 1 is straight up in the air. Okay, so it's going straight up. Number 2, I have to break into the components. Number 3 is straight to the right, which is straight in the x direction. And now we got to do the components on that one. So I got the angle on the screen. I'm going to go cos of that angle times 265, 265.96. That is 212.77. And we'll go back to that angle again, 36.8698977. I'm going to hit the sign button. And I multiply by the 265.96. And that's 159.58. We're going to add them up, just like we always did. So 159, 58, 738.8 is 898.38. That's my y direction. And my x direction is 628.33. So it's definitely going more up than down. Let's draw this in, my up and my sideways, 898.38. This would be 628.33. And I'm looking for that force here, my resultant. Square the one side, square the other side, add them up, square root them, and we get 1,090 newtons. The angle, you can figure out the angle, but then that's going to be subtly different for each side. But the magnitude's going to be the same. Okay, that's number 4 down. Let's take a look at number 5. You're standing 3-4 meters from a sphere. Okay, I I got a sphere here, just got charge on it. 7.45 times 10 to the minus 3. That's actually pretty big. Usually around minus 5, minus 6. I'm standing 3.4 meters away, right at that spot there. What's the field strength? What's the electric potential or the voltage at that point? And if you had a charge of this much, what would your potential energy be? So we're going to go through 3 different formulas here. Let's go A. Field strength is, okay, because field strength says, what would be the force on a 1 coulomb charge? Just like gravity's field was what's the force on a kilogram, his electrostatics will say what's the force on a coulomb. So that's why the 1's not there. It would really be a 1 in brackets there. So we can figure that out. 8.99. The charge is 7.45 times 10 to the minus 3 over top of 3.4 squared. Okay, it's a positive charge. So if this guy was a positive test charge, it would be going to the right. But I don't think the question really says, didn't tell me whether I'm above or below or around, so I think they're just looking for the magnitude. 8.99 exponent 9, 7.45 exponent 3 times 3.4 squared, divide, and I get a magnitude of some huge gargantuous number. Maybe we're going to go to the scientific notation world. 5.79 times 10 to the 6 newtons per coulomb. Okay, it is a huge number because we don't run into 1 coulomb charges. That's extraordinarily big. So let's take a look at B. What's the electric potential or the voltage at that point? So that's basically saying, what would the potential energy be for a 1 coulomb charge? And we know that potential energy is Q1, Q2 over R. No R squared, just an R this time. I'm actually jumping to C, but let's do B. B says that guy is a plus 1 coulomb charge. When you multiply by 1, it just disappears. So we can say voltage equals KQ over R. So we know Q, 7.45 times 10 to the minus 3. And the radius, not squared, just leave it alone this time. And we got 7.45 exponent 3 times. Oh, it's another huge number. Maybe I'll go back to scientific notation. 1.97 times 10 to the 7 joules per coulomb. Okay, so if we go to question C, we got 2 choices now. I can actually go back to the whole monster formula again. Okay, but this says if you have a 1 coulomb charge, this would be it. So you can also find force saying field strength, not field strength, sorry. You can find the energy. Is it asking? Yeah, it's asking for energy. Energy equals Q times V. I have the voltage. I'm not dealing with a 1 coulomb charge. I'm dealing with this really small one. We can stick that in. 1.56 times 10 to the minus 4. Okay, so basically, I'd be putting, instead of a 1 here, I put that number there. You could do all the math again, but I've already done the first 3 characters there. So, and that number's sitting right on my screen. So now I just type in 1.56 exponent 4 negative multiplied, and I get 3,007. I can write that one out. Joules. Okay, let's take a look at number 6. Okay, number 6. A proton is accelerated from rest through a potential difference of 450 volts. Got to remember volts means joules per coulomb. And a proton has a charge of 1.6 times 10 to the minus 19 coulombs. Very small fraction of the whole voltage. It says, what's its velocity? Oh, we'll need to know the mass too. This stuff would be given to you if you needed it on a test. That's the elementary charge of an electron or a proton. So let's find out how much energy. Okay, because voltage is per coulomb, but we're only dealing with this size. It's going to get its pretty small share of the energy that a whole coulomb would get, because that's a small fraction. So we got 1.6 exponent 19 times 450. That comes out to 7.2 times 10 to the minus 17 joules. Not much energy, but that energy is going to be used to accelerate this guy. So all of this energy is going to turn into kinetic. Okay, so we got the energy. 7.2 times 10 to the minus 17 equals 1.67 times 10 to the minus 27 v squared all over 2. That number's sitting on my screen, so I'm going to multiply by 2 and then divide by the mass of the proton, and then have to square root that number, and we get this huge answer. Maybe I'll put it in scientific notation again. Velocity equals 2.936 times 10 to the 5 meters per second. Probably too many significant digits. 2.9 is probably enough. Okay.